Welcome to This Explainer. So, to kick things off, I want you to picture a really unexpected setting for a tech story. A grand, quiet Victorian library right in the heart of London. Just imagine it, a place where craftsmanship is literally the only thing that matters, and perfection is just expected. Today, we're bringing that vibe into the cloud. We're going to follow two engineers, a junior named Timothy and a senior named Margaret, to see exactly what happens when supposedly flawless, perfect serverless architecture meets a controlled burn. Yep, we're talking about the ultimate stress test for your environment. So, set the scene. Our junior engineer, Timothy, is leaning back in his chair. He's feeling pretty invincible. He's staring at his CloudWatch dashboards, and they are just beautifully flat and green. His continent-spanning serverless setup is fully deployed. FinOps is happy with the budgets, and his dead letter queues are completely empty. He proudly tells anyone who will listen that his system is bulletproof because, well, he wrote the CDK code perfectly. The logic is mathematically certain, right? But then Margaret, his senior counterpart, walks by, looks over his shoulder, and drops this absolutely brutal truth on him. Hope is not an engineering strategy. You can't just cross your fingers and hope your systems will hold up when things go off the rails. And that leads right into the core of Margaret's challenge. She asks Timothy a question that honestly should make every single cloud architect sweat just a little bit. She says, how do you actually know your multi-region failover will kick in when a real US East 1 outage hits? Timothy immediately gets defensive. He's like, well, the Route 53 health checks are configured, so obviously the traffic will just seamlessly route over to Oregon. But Margaret hits the nail on the head here. She reminds him that cloud architecture isn't a mathematical proof. It's a living, breathing ecosystem, and it is entirely subject to the incredibly chaotic reality of the internet. This brilliantly illustrates the exact trap Timothy has fallen into. Think about it this way. He has spent months, literally months, building the most complex, incredible array of fire extinguishers. He's got the alarms, the failovers, the intricate routing logic. But he has never actually started a fire in the building to see if anyone knows how to use them, or, honestly, to see if they even spray water. Having all these fancy tools is really only half the battle. Proving they actually work under pressure is what stops your building from burning to the ground. Okay, so what's Margaret's big solution to test all these fire extinguishers? Chaos engineering. Instead of waiting around for that dreaded, catastrophic 3 a.m. emergency on a holiday weekend to find out if the failover actually works, they are going to intentionally break US East 1 right now, today, in broad daylight, while they are fully awake, highly caffeinated, and watching the monitors. That is the entire philosophy behind chaos engineering, right there. It's all about proactively injecting failures so you can discover your systemic weaknesses before those weaknesses discover you. To actually pull this off, Margaret fires up the AWS console and navigates over to a service called the AWS Fault Injection Simulator, or FIS for short. This is a fully managed service designed specifically for this exact kind of controlled chaos. It gives engineering teams a way to safely and securely simulate real-world outages. We're talking about spinning up API throttling, sudden database termination, crazy CPU stress, or network latency. And the kicker? You do it right in your production environment, but in a highly controlled and audible way. Now, at this point, Timothy is understandably freaking out just a bit. He asks, shouldn't we definitely run this in the staging environment first? Margaret calmly replies that sure, staging proves your configuration, but only production traffic reveals your production weaknesses. But before she even thinks about pressing a button, she lays down the golden rule of executing a game day in production: strict cross-team communication. She's already pinged the customer support team. She's notified the on-call engineers. Why? Because a coordinated chaos experiment is an incredibly valuable engineering exercise. An unannounced one? Well, that's just a panic attack for everyone involved. So let's look at how they actually set this up. Margaret defines a new FIS experiment template, and she strictly follows the 3 unbreakable rules of chaos. First up, you start with a clear hypothesis. For them, it's simple. If the primary API fails, traffic will route to Oregon. Second, you have to minimize your blast radius, drawing very strict boundaries around what you're messing with. And third, and guys, this is absolutely crucial, you always have an automated stop condition. In FIS, that means linking an automated abort button straight to a CloudWatch alarm. If their failover fails and global revenue starts tanking, that alarm triggers, FIS instantly aborts the experiment, and the API comes right back. They are in complete control the whole time. All right, with those heavy safety nets firmly in place, Margaret clicks Start Experiment.
And bam, instantly the primary API gateway over in Virginia just starts vomiting massive, terrifying spikes of 500 internal server errors directly at their live customers. Despite all his earlier confidence, Timothy's heart starts racing. The fire has officially been started.
Timothy is practically glued to his monitors, narrating the chaos as it unfolds. Within seconds, the Route 53 health checks start dropping. 1 failure, 2 failures, 3. And then, suddenly, the DNS switch flips. He scrambles over to the Oregon dashboard, and instantly, he sees traffic flooding into the US West 2 standby compute layer. And you know what the most beautiful part of this whole thing is? Because their DynamoDB global table was already synchronized in the background, every single customer's shopping cart remained completely intact. Total downtime? Less than 90 seconds. A few minutes later, FIS automatically stops those API errors, and traffic just smoothly routes right back home.
Timothy slumps back in his chair and lets out this massive sigh of relief. It actually worked, he says. Margaret just smiles and replies, "Now you know it works." This right here, this is the fundamental transformation. Timothy moved away from theoretical resilience, relying entirely on those flat dashboards, untested logic, and supposedly perfect CDK code. He moved to proven resilience. He used AWS FIS to intentionally break his own architecture, and by doing that, he verified his reality.
It's a pretty powerful lesson from that grand Victorian library that applies directly to our modern cloud environments. You can build the most elegant, theoretically sound systems in the entire world, but until you test them under fire, you are literally just operating on hope. Thanks so much for joining me on this explainer today. I want to leave you with one final, absolutely vital question to ask about your own cloud architecture, your applications, and your failovers. Are your safety nets just theoretical code sitting in a repository somewhere, or have you actually proven they can survive the chaos?